To start off section 4.2, we're going to pick up where we left off. So we were talking about finding where a function is concave up and concave down. Now we're going to use concavity to define the second derivative test, which is another way for us to find the local extrema, or local minimums and maximums of a function. So, to start off, the first thing that we have to do is find f prime of x and f double prime of x. Once we find them, we will find all of the critical numbers, which we call x equals c. So all the critical numbers c of our function f, such that f prime of x is equal to 0. I apologize for the scribbled out part here. So we're finding all the critical numbers of f such that f prime of x equals 0. And we need to make a note, we do not care when f prime of x is undefined. So remember, when you would find partition numbers and then critical numbers from those partition numbers, you would find all of them where the numerator and denominator of your derivative equals 0. Well, we don't care about when the denominator equals 0 for the second derivative test. From there, we are going to find f double prime of c for all c values. So every critical number you find where the numerator, the top of the fraction, is equal to 0, you're going to plug every one of those critical numbers into the second derivative. And when you do, we have three cases that come up. The first is that f double prime of c is less than 0, meaning you get a negative result when you do this. If f double prime of c is less than 0, then that means you have a relative max, or a local max. Think about why that is. If f double prime is less than 0, that means it's concave down. If it's concave down, it looks like a frown. And if it's a frown, that means you have a maximum value. Likewise, if f double prime of c is greater than 0, then f has a relative minimum at that critical value. And again, if the second derivative is greater than 0, that means you have a smile. And if you have a smile, that means you're dealing with a minimum. And finally, if f double prime of c is equal to 0 or does not exist, the test is inconclusive. So this is what I spoke about in the first video, where the second derivative test isn't technically as useful as the first one, because while it will go a lot faster, you can end up doing all this work and then getting a result that tells you you have to redo this with the first derivative test. Now we'll go ahead and try an example on this. So for this example, again, the first thing that we need to do is find the first and second derivatives. So f prime of x, the derivative of x cubed is 3x squared. Notice this is the example from the first video of section 4.2. So we'll just go through this a little quicker. The derivative of minus 3x squared is minus 6x. The derivative of minus 24x is minus 24. And the derivative of 32 is just 0. Now f double prime of x, the derivative of 3x squared, again you multiply the 2 out front and subtract 1 from it. That just gives us 6x. The derivative of minus 6x is minus 6. And the derivative of minus 24 is 0. So we now need to find our critical numbers of the first derivative, but only the critical numbers that cause it to equal 0, not where it would be undefined, meaning where the denominator would be 0. Well, we don't have a denominator in this case, so that doesn't really matter. So we have 3x squared minus 6x minus 24 equals 0. We're going to solve for x. We're going to factor this. You could also use the quadratic formula if you're more comfortable with that. When we factor out a 3, we get 3 times x squared minus 2x minus 8 as we divide each of these terms by 3. And now to factor x squared minus 2x minus 8, we'll use guess and check. We need two numbers that multiply to give us x squared, that's x, and two numbers that multiply to give us negative 8 and add up to give us negative 2. Well, that would be negative 4 and positive 2. Negative 4 times positive 2 is negative 8. Negative 4 plus positive 2 is negative 2. And now we set each of these factors equal to 0 to find our partition numbers. Remember, we don't have to set 3 equal to 0 because that can never be true. So when we solve for x in each case, we'll add 4 to each side. We'll add, that should be a plus 2, I apologize. We'll subtract 2 from each side, which gives us x equals positive 4 and x equals negative 2. These are partition numbers. Now we just need to decide whether or not they are critical numbers, and we can do that pretty easily by just plugging them back in to the original function. So, if we find f of negative 2 and f of positive 4, plugging in negative 2 into the original function, we get negative 2 cubed minus 3 times negative 2 squared minus 24 times negative 2, all plus 32. If you plug that into a calculator, you would end up getting 60. And likewise, if we plug 4 into that same formula, so 4 cubed minus 3 times 4 squared minus 24 times 4 plus 32. Then again, if you plug that into a calculator, you'll get negative 48. Okay, so from here, both of these are real values. They check out, which means they are both critical numbers, and we can use the second derivative test to decide whether they are minimums or maximums. So the second derivative test says we have to test them in the second derivative. That's just a tricky way that I figured out how to memorize this. It might help you. Just to always remember to test them in the second derivative. That's why we call it the second derivative test. So, f double prime of negative 2 means we're plugging negative 2 into 6x minus 6. We get 6 times negative 2 minus 6. That is going to end up giving us negative 18. That's less than 0. So what does that tell us? The second derivative is less than 0. That means it's concave down. It looks like a frown. So we have a maximum, a local maximum or relative maximum. Now the same thing for 4. We plug 4 into the second derivative. We get 6 times 4 minus 6, which ends up giving us positive 18. Because that's greater than 0, it's concave up. And if it's concave up, it looks like a smile. we have a local minimum. And that tells us everything we needed to solve this problem. If we go to the points we found, -2, 60, when we plugged our critical number -2 back into the original function, -2, 60 is a local maximum or relative maximum, and 4, -48 is a local or relative minimum. Now from here, I'm going to go ahead and have you all try the next problem. We have f of x equals 4x squared minus 1. Again, we are finding the relative minimums and maximums using the second derivative test. Go ahead and take a moment to try that out. Pause the video. Okay, so now going through this, f prime of x, the derivative of 4x squared, we multiply the 2 out front, gives us 8, and subtract 1 from the exponent, we have 8x. The derivative of minus 1 is just 0, so we're left with just 8x. We then take the derivative again. The derivative of 8x is just 8. And now we find our critical numbers. So remember, the critical numbers come from the partition numbers of the first derivative. So we take our 8x, and we're only finding the critical numbers for which the numerator is equal to 0. Again, in this case, there is no denominator to worry about. But even if there were, if it were something like just a side problem over here, x plus 1 over x plus 2, ignore that x plus 2. You're only setting the x plus 1 or the numerator equal to 0 when you do this on the second derivative test. So again, we're setting this 8x equal to 0 to find the partition numbers. So we'll divide each side by 8 to get the x alone, which leaves us with x equals 0. And now we need to see if it is a critical number, because right now it's just a partition number. So we plug it back into the original function. F of 0 equals 4 times x squared minus 1 is 4 times 0 squared minus 1, which just leaves us with -1. That is a real value. It checks out. So it is a critical number. That means we can test it in the second derivative. So we get f double prime of our critical number 0. F double prime of anything is going to be 8. It doesn't matter what the x value is. So because it's 8, that means it is greater than 0, it's positive. And take a moment to think about this. If the second derivative is positive, that means it's concave up. If it's positive, it's smiling. So if it's concave up, that means we have a minimum, a relative minimum. So the point that we found, 0, -1, is a relative minimum. And that is the only relative minimum or maximum in this problem.